Hi everyone, we are going to pick up with section 10.3, which is polar coordinates, and it's just a different way of graphing. Instead of having an x and a y coordinate to go left or right or up or down, we're going to look at polar coordinates, which will tell you a certain distance to go out and then a rotation around. So it's just a different way to graph. So the polar coordinate system, like I was saying, instead of an xy point, you end up with a point that is an r and a theta. Uh-oh, I just drew all over the screen. Let me erase this little black line. I don't know what that there is for. Or, there we go. The r and the theta tells you how far to rotate with the theta down here in the corner, and how far out from the origin or the pole is what we call it here. This is this O point, that's your pole. How far out from the pole to go, and then how far around to rotate. Just like in trig, positive angles rotate toward a counterclockwise direction. Clockwise would give you the negative angles. If your r is a positive, then this r theta lies in the same quadrant as theta. But if your r is negative, this point r theta goes in the opposite quadrant as theta. So opposite quadrant would be, if you remember your quadrants, your coordinate system has the 1, the 2, 3, and 4. An opposite quadrant would go from 1 down to 3, or 2 down to 4, or the other way around. And unlike xy coordinates, polar coordinates have lots of different representations. So if you had an xy coordinate, a point that said 2, 3, there's only one spot in the entire plane where 2, 3 would lie. That's not true in polar coordinates because as you rotate around, you might remember from trig, after 2 pi rotation, you start repeating, and so that's why you end up with periods and such, like from trig. So that will happen here in the polar coordinate system. So we're going to start off with plotting some points here. And so the first point we're going to pick is the point 1 and pi over 4. Now remember from trig, this would be 0 radians. Pi over 2 would be up here. Pi down to 3 pi over 2 and back around to 2 pi. So that would be your angle measures going around, starting on the x-axis, going counterclockwise. Our angle is what we usually start with first, so we're going to put the pi over 4 on there to begin with. So pi over 4 is halfway between 0 and pi over 2. It would be right in this area. That would be where pi over 4 is. Now the point 1 doesn't mean, this 1 right here for your r, doesn't mean that you go out to 1 on the x-axis or out to 1 on the y-axis. This is very much like a 45, 45, 90 triangle. But instead of a side length of 1 and 1, and then the hypotenuse would be root 2, you need an angle, or a triangle basically, of a hypotenuse of 1, and so your legs would be shorter. So the point 1, 1 would not work to plot that. You're actually going somewhere about right here, a little bit before you get to 1. The reason is because if you think of it as a triangle, you have to have a length of a side. If this is 1, these two sides are actually root 2. This is the point. If you did it in Cartesian xy coordinates, this is the point. Oh, sorry, I left the 2's off. It's square root 2 over 2. Well, it won't let me write it. There it is. Root 2 over 2. Or 1 over root 2, whichever one. But you're actually getting about 0.7 for the length of each side. And then the hypotenuse is the 1. The 1, this 1 in our point over here, is the length of the hypotenuse. And so the point would be right there. Now you could find that point in many different ways using Cartesian coordinates. For instance, you could also plot the point 1, 9 pi over 4. And it would be the same thing. You would just be going around past 2 pi to get to that point. Or you could also plot the point -1, 5 pi over 4. And it would be the same spot. 5 pi over 4 is actually down this direction. This is 5 pi over 4. But the fact that the r is negative just tells you to go in the other into the opposite quadrant. So instead of this being in quadrant 3, you would go back to quadrant 1 to get to that point. So that's how the negative works on there. And that, let me erase this part. That would be 2 additional points that would end up in the same location. So let's try the point for B here. You have 3 pi over 2. 3 pi over 2 is actually the negative axis for the y-axis. And we have a -2. This -2 right here tells me to go 2 units the opposite direction. So instead of going down towards 3 pi over 2, I'm going to go up 2 units this direction. And so at this point, the length 2 is okay to use because it's actually on the axis. And then 2 additional points, you might notice that since it's going towards pi over 2, I could do the point 2 pi over 2. That would be an additional point that would be in the same spot. Or, if you want another negative one, you could go to 7 pi over 2. Just adding 2 pi to our 3 pi over 2 to get 7 pi over 2. As long as you do a multiple of 2 pi, you'll end up in the same spot. Okay, what about 3 negative pi over 3? Well, negative pi over 3 would actually be down in quadrant 4. Remember, pi over 3 would be kind of up this direction. This would be pi over 3. The negative tells you you're going down to negative pi over 3, which would be more or less down this way. It's actually the same angle as 5 pi over 3. Now, the r is positive, so that means you go towards that angle. And so we're going to go out a length of 3, which would probably be somewhere about right here. Maybe a little bit further, kind of depending on how big you make your dot. But that length should be a length of 3 for that angle. And so our point would live somewhere about right there, towards negative pi over 3. Now, as far as the 2 additional points, well, I told you that's actually the same spot as 5 pi over 3. So we could use the 5 pi over 3 angle and say that this is 5 pi over 3. And that would be an okay angle to use. Or we could also use, do a -3 going in the opposite direction, maybe 2 pi over 3. That would be an angle in quadrant 2 that I could use. And then we could do the same thing with the 2 and the 5 pi over 6. 5 pi over 6 would be kind of an angle out this way. This would be 5 pi over 6. It's in quadrant 2. We go a length of 2, no switching back and forth here, so a length of 2 might be out to about here or so. And so that would be our different points. And that's how we would draw those points on there. So hopefully that makes some sense. Let me do the 2 different values here that would give me that same thing. You could add 2 pi to it. And if you added 12 pi over 6 to 5 pi over 6, that would be 17 pi over 6. Or you could go in the opposite direction and do -2 and either do negative pi over 6 or 11 pi over 6. You know, lots of different options. There's not just one answer here. So let's keep going. So I kind of mentioned this, but the connection between polar and Cartesian coordinates all come from trig. So in trig, your cosine is your x over r. So we change that to x equals r cosine theta. We actually talked about that when we talked about circles in the previous section. Same thing with sine. Sine would be y over r. So y equals r sine theta. And from trig, you also know, like for a circle in standard position, x squared plus y squared equals an r squared. So our tangent theta would be y over x. So we'll use these formulas along the way as well. So here, it says plot the points whose polar coordinates are given and find Cartesian coordinates using the same point. So for this first one, notice it's 2 and 3 pi over 2, because remember, this is 0 up pi over 2, this is pi, this is 3 pi over 2, the 3, and 2 pi. So if I plotted that point the way it is, 3 pi over 2, that means I go towards 3 pi over 2, 2 units. I'm at this point right here. But I could change that point back to a Cartesian point by saying that x equals r cosine theta. So my r is 2, my theta is 3 pi over 2. Cosine of 3 pi over 2 is 0. So this is 2 times 0, which is 0. And my y would be r sine theta, or 2 sine 3 pi over 2. But sine of 3 pi over 2 is negative 1. So this is negative 2. So I have the point 0, negative 2, which is where I ended up if I graphed it as a polar point as well. Let's do another one. How about the root 2 pi over 4? Now, some people, especially if it's not on an axis, don't like trying to figure out exactly how long the radius would be. So you could always change it back to xy's and then plot it if you wanted to. But pi over 4 is, like I said, in this first quadrant, that diagonal, halfway between 0 and pi over 2. And we're going to go out a length of root 2. That's actually this point right here. That's the point 1, 1 if you did it in xy coordinates. Because your x would be your r times cosine pi over 4. Well, cosine pi over 4 is root 2 over 2. And if you do root 2 times root 2 on top, you get 2 divided by 2, which is 1. And if I did y, you would end up with the same thing. It is r sine theta, but sine and cosine have the same value at root 2 of root 2 over 2 at pi over 4. And so this would also be root 2 over 2, which is 1. So this point is the point 1, 1. Or if I do one for C, negative 1, negative pi over 6. Negative pi over 6 is in quadrant 4. We go out 1 in that direction. So you're going to end up somewhere, I believe, in between 1 and 2 on the x-axis down just a little bit. But let's flip it and find the xy part first and see what happens. So my x would be r cosine theta. Since cosine's an even function, on an even function, the negative would not matter. And so the cosine of pi over 6 and the cosine of negative pi over 6 are the same thing. Or if you want to do 30 degrees or negative 30 degrees, doesn't really matter. But at 30 degrees or pi over 6, cosine is root 3 over 2. So I get a negative root 3 over 2. And then y would be negative 1 times sine negative pi over 6. Sine is an odd function, so that negative will get factored out in front to become positive. And so we'll end up with a positive 1/2. So a negative root 3 over 2 and a positive 1/2. I'm so sorry. I shouldn't have laughed. there's a woodpecker that just flew into the side of my house out here on the porch, and so a woodpecker just hit the side of the house, and it was kind of funny. But anyway, the point would be negative root 3 over 2 and then 1/2. So we're going to go negative root 3 over 2 or square root of 3 over 2. Doesn't really matter. Is going to be, oh, sorry, this is actually in quadrant 2 because of the negative on the 1. That woodpecker is bothering me. So he just flew by again. Root 3 over 2 would be about 1.73 or so. So you're actually going to end up about right here. Up a half and to the left 1 over root 3. If you did it in a polar equation, the negative pi over 6 is in quadrant 4, but the negative on the 1 tells you to go the opposite direction. That's why we're in quadrant 2. Okay, this says find, you have 2 Cartesian coordinates given. Find a polar coordinate where r is greater than 0 and where r is less than 0 for thetas between 0 and 2 pi. And so now we're going to use our other formulas. If you have 2 points, or an x and a y here, we're going to use our formula that x squared plus y squared equals r squared to find the radius. So we'll have negative 4 squared plus 4 squared. So that's 16 and 16, or 32. So if I take the square root on both sides, keep in mind here, the radius is always positive, so we're not going to do a plus or a minus. 32 is 16 times 2. This is 4 root 2. In fact, you might remember from trig that if you have a point, an xy point, where the values are the same for both x and y, regardless of whether or not they're positive or negative, then the radius is always that number times the square root of 2. And for the other part, to find the angle, we're going to use our formula that tangent theta equals y over x. And so here we'll have tangent theta equals y over x. So tangent theta is -1. Theta is -1 in 2 locations. That could either be in quadrant 2 or in quadrant 4. In quadrant 2, you're looking at 3 pi over 4. In quadrant 4, you're looking at 7 pi over 4. But this point, -4, 4, this has to be a quadrant 2 angle, which means I don't want to use the 7 pi over 4. I want to use the 3 pi over 4. And so my point on this one actually is the point r 4 root 2 theta 3 pi over 4. And so that would be a representation for the point with a positive r. And then I could also do a negative r as well and say that it's -4 root 2. Remember, the length doesn't change. The opposite just comes from the negative in front. And I could pick the other angle, the 7 pi over 4, so that I could push it back into quadrant 2 using the negative on the r. So that one's hopefully not too bad. Let's try the same thing on the next one. If I do my x squared plus y squared equals r squared, I'll have 3 squared plus 3 root 3 squared equals r squared. This is 9. 3 squared is 9, and the square root of 9 is, square root of 3 squared is 3. So 9 times 3 is 27, and one additional 9 would be 36. So r is 6. That one came out really nice. Then for the angle, I would do tangent theta equals y, which is 3 root 3 all over 3 for the x, or tangent theta is the square root of 3, which is good. That's a really nice angle to work with. Tangent is root 3 at pi over 3. It's also root 3 Since tangent's positive in quadrant 1 and in quadrant 3, you could have also done 4 pi over 3. And it just kind of depends on where the point's located. This point is in quadrant 1. And so I'm going to not use the 4 pi over 3. I'm going to use the just pi over 3 and come up with an angle and a r of having 6 and pi over 3. If you want to do the negative of that one, I could do negative 6 and use the other value of 4 pi over 3. And that would be 2 points. That would give me the same location. Okay, this one says sketch the region of a plane described. You have a plane where the radius is between 2 and 3, and your angles are between 5 pi over 3 and 7 pi over 3. Well, the angles of 5 pi over 3 and 7 pi over 3. 5 pi over 3 would be kind of this direction. And forgive me, that's supposed to be a straight line. But this would be 5 pi over 3. 7 pi over 3 is actually the same location of just pi over 3. You just rotate it around one additional time. And we're looking for a radius between 2 and 3. So between 2 and 3, I need a region that would be between those two numbers, bounded between those two angles. And so to keep the radius the same all the way across, you'd have to have a radius of 2 and a radius of 3 all the way around. And so our region would be anything inside here. And that would be my region described by that radius and those angles. Okay, this says identify the curve by finding a Cartesian equation for the curve. So instead of putting a polar equation there, we're going to put a Cartesian equation there. And so you have to kind of manipulate it and using either an identity or some other sort of manipulation to come up with, could I change this to a Cartesian equation? So for this first one thing that I notice is that cosine 2 theta has an identity for it. This thing right here, there's a trig identity that says cosine 2 theta is cosine squared minus sine squared. So I'm going to put that in here. I'm going to say this is r squared times cosine squared minus sine squared. Now, is this the only way to do this problem? Possibly not, but it's what I see the quickest. And so if you Google it or something, you might find a different method to do it. But I could multiply the r squared across and say that this is r squared cosine squared minus r squared sine squared. And the reason why I want to do that is because then the r squared and the cosine squared is the same thing as r times cosine all squared. And then I'll have r times sine all squared equals 1. And I know that r cosine theta is our definition for x, and r sine theta is our definition for y equals 1. So this is my Cartesian equation for the same graph. A lot of people don't know, when I've taught this in class, a lot of people don't know what equation that is. A lot of them will say a circle. It's not a circle because it has to have a plus sign in between to be a circle. So if you don't know, this is actually a hyperbola. It's a hyperbola centered at the origin, not shifted one way or the other. Let's look at the other one down below that. R equals 5 cosine theta. I can't read really. I'm trying to get it just like that first one. I want to try to get it to be r cosine theta. And I can't get the r and the cosine that's already there in it to become next to each other. I could do r divided by cosine, but that doesn't do me any good. I have to have r times cosine. So there's nothing in the cards that says I can't take this entire equation and multiply it by an r. And if I do that, I'll get that r squared equals 5r cosine theta. That's perfectly legitimate. Then I know that this thing right here is x, and I know r squared is x squared plus y squared. And so I could rewrite this to be x squared plus y squared equals 5x. And so you could actually leave it like that, or if you want to figure out even more detail, you could subtract the 5x over and say this is x squared minus 5x plus y squared equals 0. And you could complete the square. It's actually a circle. You can complete the square taking the 5, taking half of it and squaring it and adding it to both sides. And you could make this say x squared minus 5x. 5 squared would be 25, so I'd have 25 over 4 plus y squared equals 25 over 4. So I just added that same thing to both sides. And so the left-hand side actually factors as x minus 5 halves all squared plus y squared equals 25 over 4. This, actually anything, this would be the equation, or if you want to have more detail with it, you could pick this one over here. But either one, this is a circle. It's a circle centered at the point 5 halves 0, because of the 5 halves subtracted from the x, with a radius of 5 halves as well, because of the square root of the 25 over 4. So hopefully that's not too bad. Let's go the other way around. Find a polar equation for the curve represented by this Cartesian equation. So hopefully this first one's pretty easy. This is just a straight line. This is a linear equation with a slope of 3, with a y-intercept of 1, and we're going to change that to be a Cartesian equation. Change it to a polar equation. Excuse me. So every x and every y has a formula for it. So we'll change the y to r sine theta, and we'll change the x to r cosine theta. And ideally, when we do this, we'd like to try to get it to be r equals something, just like we have it y equals something. That's usually the best you could probably get. You can't always do that, but I'll show you what happens if you do that here. I could subtract the 3r cosine theta to the other side. Factor the r out. And then divide them across. So I'd have 1 over sine theta minus 3 cosine theta. This is what a straight line looks like in Cartesian coordinates, which is kind of weird, but it's okay. The next one hopefully is not too bad. X squared plus y squared equals 2 times c times x. The c is just a number, so we don't have to do a whole lot with it. But I remember that x squared plus y squared, this is r squared, so I can just go ahead and plug that in. And this x on the other side will turn into my r cosine theta like it did up above there. And so this will become r squared equals 2 C R cosine theta. That's what your x will become. And so here what we could do is divide by r on both sides to cancel the r off. And you just end up with r equals 2c cosine theta. And that's basically just a circle. Okay, would it be more easily to make this type of equation as a polar equation or a Cartesian equation? So if you had a line through the origin making an angle of pi over 6 with the positive x-axis, would it be easier to do that with a polar equation or a Cartesian equation? And if you ever have anything that starts out with, you have a certain angle, it's probably going to be polar. And so in this case, it would be. You're looking at a polar equation here. But if you were doing a vertical line through the point 3, 5, vertical lines, you might remember from algebra, are extremely easy to do because a vertical line is just x equals whatever the x coordinate is. So the point would be x equals 3, would be the equation of the line as well. So that would definitely be a Cartesian equation, not a polar equation. Polar equations have arcs in them because of the rotation of the angle. If you have a straight line, it's almost always easier to do it in Cartesian equations. Okay, so there's a bunch of graphs that have basically graphs that pop up a lot. And so circles are one of them. A circle is going to be represented by a number times either sine or cosine. The cosine would be the one on the x-axis. That's this one here. The sine would be on the y-axis. Those two are very popular. They'll pop up a lot. Then we have what we're called lemniscates. A lemniscate is basically an infinity sign. The sine one, right here, is at a 45-degree angle. And the A, it tells you how long the loop is. The cosine one is actually on the axis. That one is actually easier to draw. And we actually kind of drew one in the last section, if you might remember that. Then you have limicons, or limicons. The C is a soft C, limicon. And limicons come in different pictures from different values that are in front of them. So you have an equation that you'll either have A plus or minus B cosine theta or sine theta. The cosine, these are all cosine representations on the right-hand side here. Cosine, just like with the circle, will be on the x-axis. So these are all cosines. So all of these pictures are based on this equation. But if it was a sine, your graphs would be on the y-axis. That would be the difference, kind of like the circle up on the top left. If your A and your B are both greater than 0, then if you divide them, if A over B is less than 1, you'll get a loop on the inside. You'll get this picture right here. If they're exactly equal to 1, you get a very special shape called a cardioid. It's supposed to be a heart shape on the top, or on the left-hand side if you're looking at this picture. If you divide them and you get between 1 and 2 for your ratio, you get a dimpled, so it's kind of just a curved in a little bit. And if it's bigger than 2, that would be this one here. If it's bigger than 2 or greater than or equal to 2, then you get just a flattened side. So you get a convex limicon. And so that's your 4 different options. If your A is 0 and your B is 1, so that when you divide them, you actually get a number less than 1, but you actually get 0, that's your circle. You'll end up with a circle if your A is 0 and your B is, well, your B could be really anything depending on how big the radius is. But if your A is 0, you'll end up with a circle. You also have what are called rosettes or rose curves. A rose curve happens when you have a number in front of your theta. So you have something like cosine 4 theta or sine 5 theta. This is where you have multiple loops going around. Cosine will always start on the x-axis. Sine will always start off of the x-axis. So you'll notice the top two, this is cosine, and the bottom two is sine. The first one, this is actually cosine because of the 3 right here. This is cosine 3 theta. Because of the 4, this is cosine 4 theta on the top right. If you have an odd number, the odd number you have is the number of petals you have. But if you have an even number, you have to double the amount of petals you have. That's why 4 gives you 8 different petals on that curve. Same thing on the sine. This is sine 5 theta, so we end up with 5 petals. This is, sorry, sine 5 theta. This is sine 2 theta, which gives you 4 petals because it's even. So we're going to try to graph some of these type things. Now, when you graph a polar equation like this, there's two schools of thought. One school is to do it by graphing what that Cartesian equation would have looked like, and then turning it into something else, turning it into the polar equation. So, like for instance, r equals theta. That's basically like y equals x. If I did that as a Cartesian equation, I would just have a straight line. For every y, you'd have an x, the same value. For every r, you have a theta, same value. If I was to translate that over to every r and every theta have to be the same in a polar equation, then I would start at the pole. When r is 0, theta is 0. And so with a radius of 0, you're just at the pole. And then you might go around the circle. Okay, so when you get to pi over 2, you're at pi over 2. So if I was at pi over 2, the angle says to go up to pi over 2. So that's angle right there. Then I would go over to pi. So my direction, remember these axes, this is 0, this is pi over 2, this is pi, this is 3 pi over 2, this is 2 pi. So if I plugged in pi, I would go the pi direction, pi units. That would be right here. If I went to 3 pi over 2, I would go down to 3 pi over 2 in the 3 pi over 2 direction. That would be right here. If I went to 2 pi, I would go out to 2 pi in the 2 pi direction. That would be right here. And so you actually end up with a curve that does, ooh, that looks awful. That was supposed to go more up than that. Try that again. My drawings are not very good, so I apologize. And so we'll get kind of a looping thing. This is supposed to be a nice smooth curve, but it's really not. And so we get a graph that kind of looks something like that. So if we kind of take that same idea and do it with, say, 3 cosine 3 theta, 3 cosine 3 theta tells you cosine starts at a maximum, if you remember in trig, goes down to the axis, all the way down to the min, back up to the axis, and back up. This would be your cosine or graph stretched out by 3. And it would look something like this. But we have cosine 3 theta. Now in trig, what that meant was you're going to take this number and divide it by 2 pi. So your period would be 2 pi over 3. So we don't go that far out. You only go out to 2 pi over 3. So these little tick marks across the bottom, this is in pi over 6s, 1 pi over 6, 2 pi over 6, 3 pi over 6, which would be pi over 2, 4 pi over 6, 5 pi over 6. So you're stopping here. This is 2 pi over 3. So your graph actually goes here to here, down to here, back up to pi over 2, and then back up. So our particular graph, 3 cosine 3 theta, kind of gets mushed, and it's right here. Well, kind of missed it there, but anyway. Looks something like that. So the blue one just gets condensed. Can we take this idea and move it over to here and come up with what happens for 3 cosine 3 theta? Remember, cosine always starts on the axis. So we are at 3. So over here, we're starting at 3. When we get to, oh, and by the way, if you want to see this, this is pi over 6, pi over 3, pi over 2, and 2 pi over 3. So as we get to 2 pi over 3, we've made one loop. By the time you get to 2 pi, you actually make 3 loops. It's got to come back down and back up, back down, and back up. So we got to get those 3 loops in here. So starting at 3, we're coming back down toward the axis. So you're actually going to end up with a graph that kind of goes like this. It'll go back down toward the axis at 0. Oops. Erase that part. And then it goes below the axis and loops back up to the origin. So we got to go down below the axis and loop back up. And then it goes above the axis and loops back down. And then back below the axis. Ooh, that looks awful. Before it loops back up. See if I can't erase this part here. And like I said, my drawings are pretty atrocious, so. But that's why we get 3 different loops. You have to start above the axis, go below the axis, above the axis, below the axis, above the axis, and end back where you started. And this is your 3-petal rosette that we were just looking at on the other page. They all are supposed to go through the origin right there, so that's, again, just bad drawing. But you get 3 loops. And hopefully that makes some sense. Another way you could do graphing is by symmetry instead. So symmetry says draw one of the petals and then just flip it across the origin whichever way you needed to make it. So if a polar equation is unchanged when you replace theta with a negative theta, you're symmetric about a polar axis. If you plug in different values, you can see whether you're going across the axis, across the vertical axis, the horizontal axis, the polar axis. And so we could do it by symmetry instead. And that's usually how most people would graph a polar equation. So I'll show you a couple of those as well. So this equation says, sketch the curve r equals 2 sine 4 theta. So I'm going to do this by symmetry instead of doing it in terms of a Cartesian coordinate first. So if I do this as a symmetry type problem, because this says 4 theta, that means I have to have 8 petals on a rosette. And those 8 petals have to have a length of 2. So that 2 tells you the length of each petal. Sine never starts on the axis. It starts off of the axis. So we have 8 petals. So I need 2 pi, or 360 if you want to do it in degrees, divided by 8. Every petal is pi over 4 apart. Every petal is pi over 4 apart. So I would start, sine always starts at the origin, just like it did in trig. Remember, kind of give you a short version. You know, you're looking at a graph that does like this. You're starting at the origin to make your rotation. and it'll go above the axis, then below the axis, then above the axis, then below the axis, and you got to do that enough times. And so we're going to get a graph that kind of does this, and it's going to loop. That's one petal. I need to make 8 petals based on symmetry that are pi over 4 apart. So the next one might be down here, and then over here, and then up here. There's 4 petals. But to be pi over 4 apart, you also need one here, 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 and there. That has 8 petals that are pi over 4 apart. That's how your symmetry would work. Let's do another one based on that. Sketch the curve. This is 1 plus 3 cosine theta. 1 plus 3 cosine theta. Now, when you do 1 plus 3 cosine theta, this one, if you remember back from our graphs a while ago, something special about this. This is a limison. This is your A. This is your B. So if I had to do the A over B, that would be 1 over 3. Well, 1 over 3 is between 0 and 1. So if you're between 0 and 1, you're going to end up with a loop on the inside. Since it's cosine, we're going to be on the x-axis. And so cosine will start at its maximum. Now on a limison, if it has a loop in it, so if you have a loop on this limison, if you take the two numbers, 1 plus 3 will make 4. That'll be how far out it goes. The inside part will go 1. We'll do 3 minus 1, which is 2. So that's going to be the length of the inside part. And remember, you can always just plug points in. If I let theta be 0, cosine 0 is 1. 1 plus 1 times 3 is 3 plus 1 is 4. That's why that happens. If your theta equals 0, then your r equals 1 plus 3 cosine 0, which is 4. If you did pi over 2, if you plugged in pi over 2, cosine pi over 2 is 0. 3 times 0 is 0, plus 1 is 1. So you'll have a point right here. And by symmetry, you'll also have a point that's down there as well. Remember, symmetry is very important. But we'll end up with a graph that's going to loop around this 1. Then, since it has an inner loop, we're going to go around like this, and then back to the 1 for the symmetry part. And if you're a really good artist, the top and the bottom are exactly the same, which my bottom part right here looks a little flatter than it should, but they should be exactly the same. Okay, this is r squared equals 9 cosine 2 theta. This is your lemniscate. And on this one, since it is cosine, we're going to have kind of that infinity shape going back and forth across the x-axis. If it was sine, you'd have it at a 45-degree angle. The 9 will tell you how wide it is. Since it's r squared equals 9, we're only going to go out to 3. So we'll go out to 3 on both sides. It'll make a loop-de-loop. And again, you can plug numbers in. If you plugged in 0, cosine 0 is 1. 1 times 9 is 9, so r squared is 9. That's why r is 3. If you were to plug in pi over 2, cosine of 2 times pi over 2 would be cosine pi, which would be -1, times 9 would be -9. You can't have an r squared be -9, so it can't go that direction. But we'll have a length of 3 on a loop here. And so we'll have a loop that's on this side, and you'll have a loop that's on this side. And that's what your lemniscate looks like. Now, some people try to really understand what's going on these problems, and other people just memorize that chart and say, okay, if it's got an r squared equals a number times cosine, it has to be this type of shape. You can do whichever one you think is better for you. Okay, let's talk about derivatives. If you remember when we talked about parametric equations, your derivatives are a little bit different than it is if it's Cartesian, and that's also true in polar equations. You're still after dy dx. You're still after the derivative of y with respect to x. But if you have a polar equation, then you're going to have to do dy d theta and dx d theta. Much like we did dy dt divided by dx dt. Now we're going to do thetas. So this is what you could memorize. And then you could use that x equals r cosine theta and y equals r sine theta. Do the product rule of each one, and you would end up with this equation. I always just learned this second equation right here, and I didn't worry about doing the product rule because I didn't want to do the product rule every single time I did a problem. So I just memorized that it's dr d theta sine theta plus r cosine theta over dr d theta cosine theta minus r sine theta. You can memorize that, or you can do the product rule each time. It doesn't really matter. I like memorizing them. So if it says find the slope of the tangent line to the curve, I have to find the derivative of r equals 2 sine theta. And then plug in the pi over 6. So my dy dx would be, and like I said, I just memorized this long formula, the dr d theta sine theta plus r cosine theta divided by dr d theta cosine theta minus r sine theta. The top and the bottom are the same, except you swap the sine and cosine, and you swap the sign, the positive to negative. So the dr d theta, that's the derivative of the equation that I'm working with, the 2 sine theta. So my dr d theta, the 2 sine theta, would become 2 cosine theta. And it just gets multiplied by sine theta. And then it says plus r sine theta. Well, the r is the equation, the 2 sine theta times cosine. All divided by that same thing, 2 cosine theta minus 2 cosine theta. Oh, sorry, 2 sine theta, but the wrong one. Times sine theta. And you can do as much manipulation as you want to this to make it simplify if you want to. It does simplify a little bit. The top part, 2 times sine times cosine, and 2 times sine times cosine can actually go together, or you could use it as an identity. 2 times sine times cosine is the identity for sine 2 theta. So you actually have sine 2 theta twice on the top and the bottom. The top left and right, sorry. The bottom part is 2 cosine squared minus 2 sine squared. So on the top, you could actually put those together and make this 2 times sine 2 theta. The bottom part, if you factor the 2 out in front, this is cosine squared minus sine squared. And cosine squared minus sine squared is the identity for cosine 2 theta. In fact, now these two actually would cancel if you want to cancel those off. So this is just sine 2 theta over cosine 2 theta. Which, if you know from trig, sine divided by cosine gives you tangent 2 theta. So that's the derivative, dy dx, of this equation. And then I just plug the pi over 6 in. So your slope would be tangent of 2 times pi over 6, which is tangent pi over 3, which is the square root of 3. And that would be your slope. Now, there's absolutely nothing wrong. If you wanted to, you could take this pi over 6 and just plug it in right there if you wanted to. And then simplify all the numbers instead of simplifying the trig functions. That does not matter one way or the other. But this one simplified pretty well, so I went ahead and just did the simplifying of the function itself. So let's do another one. This is 2 plus cosine 3 theta at pi over 4. So this one I'll show you. Maybe we don't try to simplify the function because it might look really messy. And so your dy dx, it is the derivative of r with respect to theta. dr d theta. So the 2 goes away. Cosine goes to negative sine. So I'll have negative 3 sine 3 theta. So it's dr d theta times sine theta plus r, which is the 2 plus cosine 3 theta, times cosine theta, all divided by the same sort of thing, negative 3 sine 3 theta times cosine theta minus, oh, I don't know why I put that extra line over there. Get that off there. Minus r times sine theta. And so on this one, you'll notice that the sine 3 theta and the sine theta, they don't go together. Or the sine 3 theta and the cosine theta, they don't go together. So you're not going to get a whole lot of simplifying out of this anyway. So why not just go ahead and say, okay, let's figure out what the slope is. And plug in the pi over 4. So this would be negative 3 sine 3 pi over 4 sine pi over 4 plus, if I multiply the cosine across, I'll end up with 2 cosine pi over 4 plus cosine 3 pi over 4 cosine pi over 4 all divided by. On the bottom, I'll have a negative 3 sine 3 pi over 4 cosine pi over 4 minus 2 sine pi over 4 minus cosine 3 pi over 4 sine pi over 4. And then, nicely, these are all numbers off the unit circle, so it's not too bad to work with. Sine of 3 pi over 4 is root 2 over 2, as is sine pi over 4. They are the same value. Cosine pi over 4 is also root 2 over 2. Cosine 3 pi over 4 is actually negative root 2 over 2. But pi over 4 would be root 2 over 2. On the bottom, I'll have a negative 3, root 2 over 2, root 2 over 2, minus 2 times root 2 over 2, minus cosine 3 pi over 4 is, again, negative root 2 over 2. And sine would be root 2 over 2. And then you just have to simplify that as best you can. Sometimes it simplifies nicely, and sometimes it just doesn't. We have a whole bunch of root 2 over 2's in there. And so hopefully this will come out kind of nice. Across the top, root 2 over 2 times root 2 over 2 would be 2 over 4, which would be 1/2. So this is negative 3/2. Then I'll just end up with a plus root 2 because those 2's cancel. And then I'll end up with a minus root 2 over 2 times root 2 over 2 again will be 2 over 4, which would be 1/2. So I'll get a minus 1/2. On the bottom, I get sort of the same thing, negative 3/2. The root 2's root 2 over 2 with the 2 in front cancels, so I'll get a minus root 2 here. And this will give me a plus 1/2. So a 3/2 and a 1/2 would be 4/2, which is a negative 2 plus root 2 on the top part. On the bottom part, negative 3/2 plus a half would be a negative 2/2, which is a negative 1 minus root 2 on the bottom. And so you could leave it like that, or if you want to cancel some of the negatives off, it's the same thing as 2 minus root 2 over 1 plus root 2. Or you could rationalize it if you wanted to. I won't take the time to do the rationalizing, but that's a really ugly slope, but that's just how it is. So hopefully that wasn't too bad. Okay, this says find the points where the tangent line is horizontal and vertical. Well, vertical and horizontal, whichever one. So r equals 3 cosine theta. Now, by what you already know from what shapes these things make, hopefully you notice this is a circle. And so if it's a circle, you should have horizontal and vertical points at the top of the circle and the sides of the circle. The sides of the circle probably at things like pi over 2, 3 pi over 2, or the top parts are pi over 2, 3 over 2, and then pi and 2 pi and 0 for the other part. So we'll see if that's what kind of things we end up with. First, you have to take the derivative. So let's start with the derivative. Dy dx is dr d theta. So the derivative of this thing would be negative 3 sine theta. So it's dr d theta times sine theta. So I have to put an additional sine theta plus r cosine theta, and divide that by dr d theta cosine theta, then make it a minus r sine theta. Now you really do want to try to simplify this if it helps, because we're going to basically take the top and the bottom and set them equal to 0 to find these horizontal and vertical points. So the top part, this is negative 3 sine squared plus 3 cosine squared. The bottom part is negative 3 sine theta cosine theta minus 3 sine theta cosine theta. So the top part, if you factor the 3 out, this is cosine squared minus sine squared. That's our identity for cosine 2 theta. The bottom part, there's a negative 3 and a negative 3 would make a negative 6. But I don't really want to make it a negative 6. What I'd rather do is to make it a negative 3 times 2 sine theta cosine theta, which is also negative 6. That way, the negative and being well, not the negative, the 3's factored out in front will actually cancel each other, and I'm left with negative cosine 2 theta over sine 2 theta. Now you could also write that as negative cotangent 2 theta. You can if you want to. I don't really need to do that because my horizontal and vertical, I need to set the top and the bottom of the fraction equal to 0. So I need to use the cosine and the sine part. So for my vertical, let's do horizontal first. To do horizontal, I want the top equal to 0. So that would be the cosine 2 theta equals 0. Now you might say, why didn't you do negative cosine 2 theta equals 0? It doesn't matter. If you're setting equal to 0, it doesn't matter if it's positive or negative. And so cosine 2 theta equals 0, where 2 theta would have to be, sorry, cosine is 0 at pi over 2, so 2 theta has to be either pi over 2 or 3 pi over 2. That's the first rotation around the unit circle. Since it's a 2 theta, we actually want to go 2 rotations around to make this a 5 pi over 2 and a 7 pi over 2. And so theta actually comes out to be pi over 4, 3 pi over 4, 5 pi over 4, and 7 pi over 4. Those are the angles. We also would like to have the actual points for the r as well. So if I was to take those points, those thetas, and plug them back in, cosine of pi over 4, 3 pi over 4, 5 pi over 4, or 7 pi over 4, they would either give you positive or negative root 2 over 2, depending on what quadrant you're in. Pi over 4 and 7 pi over 4 would come out positive. 3 pi over 4 and 5 pi over 4 would come out negative. You're multiplying that by 3, though, so we'll actually end up with 3 root 2 over 2 or negative 3 root 2 over 2. Now, on a polar equation, those points are going to match. So, for instance, if I did my r, if I plugged in pi over 4, I would get 3 root 2 over 2, pi over 4. If I went to 7 pi over 4 and plugged the value in for that and did a negative, I'd end up in the same spot. So we're not going to have to do that one. Or I could do, if I plugged in 3 pi over 4, I'll end up with negative 3 root 2 over 2. Oh, sorry, not pi over 4. I'm going to do 3. Yeah, let's do 5 over 4. So I'm going to pick those 2 points. Oh, I'm sorry. Not 5 pi over 4. I keep saying 3 pi over 4, and I keep writing the wrong point down. If I was to plug in 3 pi over 4, that would give me a quadrant 2 angle. If I did pi over 4, that would give me a quadrant 1 angle. 7 pi over 4 would give me a quadrant 4 angle. And 5 pi over 4 would give me a quadrant 3 angle. But I can get to those angles based on those other 2 points by going the opposite direction. So we only really need those 2 points. And let's do the vertical one. For the vertical, I want to set the bottom equal to 0. So this would be the sine 2 theta equals 0. Just like on cosine, that's where 2 theta, wherever sine would be 0, which would be things like 0 and pi, or 2 pi, or 3 pi. You know, you can keep going on and on and on. So those type angles. So our thetas would actually come out to be 0, pi over 2, pi, 3 pi over 2. And I'm going to do the same thing. I'm only going to plug in the first 2. And if I plug in 0, cosine 0 is 1. So 3 times 1 is 3. So I get the angle 3, or the point 3, 0. Or if I plug in pi over 2, cosine pi over 2 is 0, times 3 is 0. So I'll get the point pi over 2, 0. If you plugged in pi, you get cosine of pi, which is negative 1, which would be negative 3. But that's just going the opposite direction anyway. And pi over, the 3 pi over 2 would go the opposite direction for the pi over 2. And so those points should be where it is horizontal. Okay, let's do one more. Where are they vertical and horizontal at? So I have the point, or the equation r equals 1 minus sine theta. I have to find the derivative, dy dx, would be dr d theta. the 1 would go away. Derivative of sine is cosine, so I'll get negative cosine times sine plus r times cosine divided by negative cosine times cosine minus r times sine. Now, we need this to simplify as much as possible, and hopefully it'll simplify a little bit. Let's see. The top part is a negative sine cosine plus 1 minus sine cosine. So I can combine those together, which is a good thing. On the bottom, I'll have a negative cosine squared. Let's see, a minus sine and a positive sine squared. So we could do a little bit of simplifying here. The top part, that is 1 minus 2 sine cosine. So there's our double angle for sine again. The bottom part, I'll have a negative cosine squared and a positive sine squared. If I was to factor a negative out of that, I could make this negative cosine squared minus sine squared and have a leftover minus sine left over. So this is 1 minus sine 2 theta on top. Oh, I'm so sorry. It's not a 1. I didn't multiply my cosine across, did I? If you multiply the cosine across, this is an actual cosine theta sitting here. So let's put a cosine in there. Very easy to mess these things up if you're not really careful. And this is a negative cosine 2 theta minus sine theta. Which you can do that if you want to. I don't know if that'll help a whole lot because when I set it equal to 0, I don't really want those double angles in there anyway. So I might go off of the one step before that. So let's do horizontal first. If it's horizontal, the top has to be 0. So I'm going to set the cosine theta going off of this step right here. Cosine theta minus 2 sine theta cosine theta had to be 0. So there's a cosine in common. This is why I probably shouldn't have done the double angle stuff. And there's a 1 minus 2 sine theta left over. So either cosine theta is 0 or 1 minus 2 sine theta is 0. This one says, where is sine theta 1/2? Well, cosine is 0 in places like pi over 2 and 3 pi over 2. Sine is 1/2 in places like pi over 6 and 5 pi over 6. If you're looking at the unit circle. And so then if you were to plug those points back in, plugging in pi over 2, sine of pi over 2 is 1, so 1 minus 1 is 0. So I'd have the point 0 pi over 2. You plug in 3 pi over 2, sine of 3 pi over 2 is negative 1. So that would be 1 minus negative 1, which would actually be 2, 3 pi over 2. If I plug in pi over 6, sine of pi over 6 is 1/2, so 1 minus 1/2 would be 1/2. So I'd have 1/2 pi over 6. And then I'd have 5 pi over 6 would be the same thing. It would also be 1/2, so I'd have 1/2 and 5 pi over 6. Then I want to do the bottom part as well. So if I do the bottom part, again, going off of this step here, I'll have, in fact, in that case, I might as well multiply the negative back across and do, this is the vertical part over here. Vertical. I think I spelled that wrong, but whatever. You multiply the negative across. I'll have a negative cosine squared theta plus a sine squared theta minus a sine theta equals 0. It might, because they have different trig functions in them, sine and cosine, I'm going to have to change them to all be one thing. So I'm going to change the cosine squared to be 1 minus sine squared from a Pythagorean identity. And so if I multiply the negative across, I'll end up with a minus 1, a plus sine squared to go along with this other sine squared that I already had, minus sine. So you're going to end up with a quadratic equation. This is 2 sine squared theta minus sine theta minus 1. And that factors. So if we factor it, we'll end up with 2 sine theta plus 1, it looks like, and sine theta minus 1. That'll give me a minus, yeah, that's right. And so if you set each one of those equal to 0, either sine theta had to be 1, or sine theta had to be negative 1/2. Sine theta is 1 when theta is pi over 2. And negative 1/2 when it's, let's see, 7 pi over 6 and 11 pi over 6. Now, one thing you might notice is the pi over 2 popped up on the vertical and on the horizontal. It can't be a point where it's vertical and horizontal. And so if it makes the bottom 0, doesn't matter what the top is, the bottom 0 says it's a vertical asymptote. So back over here, I have to throw this point off of the horizontals. So there's 3 points where it's horizontal. And so the vertical point would be the 0 pi over 2. And then you plug in the pi over 6, the 7 pi over 6 and the 11 pi over 6. 7 pi over 6 sine theta would be negative 1/2. So I actually get 3/2. 7 pi over 6. And I'll also get 7, same thing for the 11 pi over 6. I'll get 3/2 and 11 pi over 6. And those would be my points where it is vertical. So there are 3 vertical, 3 horizontal. So hopefully that made sense. If not, let me know. I'll try to explain it again. The next section, though, is probably the longest and the most complicated for people to understand when we actually trying to find area inside of the curves. So that'll be the next one. So hopefully that's good.